Hello students, we now reached chapter 9. The topic is polyprotic acid-base equilibria. So far we have learned acid-base equilibria only for monoprotic acid and bases. Okay, monoprotic means it produce after uh, dissociation in water only one protons, or it accepts only one proton. Okay, in that case, um, the chemistry is relatively simple. Okay, but we can do many things. We can, for example, prepare a buffer solution, depending on pH. Now, yeah, we are going to dealing with more complicated equilibria. In this case, um, acid bases now produce or accept more than one protons. Okay, in that case, um, the things are more complicated. Okay, but we have a systematic approach for this equilibria. Okay, now let's start. Um, the proteins are the representative molecules for polyprotic acid and bases. Okay, the proteins are everywhere, and since you are very interested in protein, I think so. It is very important for you to have enough knowledge for proteins in terms of acids and bases. Okay, you know, proteins in this case, the acid-base chemistry is not that simple. Okay, let's start here. This is the what two. Let me see. The secondary structure of myoglobin. As you know, myoglobin in blood carries oxygen. Okay, you see this thick long line is the amino acid sequence, and in the middle of that we find this heme group. Yeah, heme group is like this one. Okay, this is heme group. The core structure is called porphyrin. Okay, and it has you see, it is very symmetric. Okay, you're considering only this part. This core part is symmetric, and electrons are well distributed along this mm, structure. Okay, like a benzene, but in this case, this pi electrons are 18. mm. Benzene's pi electrons is only 6. Okay, anyway, it has, let me see, 4 pyrrole groups. Okay, one, two, three, 4, and they are facing, yeah, together. And then inside, the structure, there is some space where the ion, okay, ion, ion is coordinated through 1, 2, 3, 4, 5 nitrogen atoms. So this structure itself, this porphyrin structure, is quite planar. Okay. Anyway, this ion now have has a very high binding affinity toward oxygen. Okay, that's why this myoglobin or hemoglobin, right, um, have ability to carry oxygen, you know, in the through the bloodstream, to everywhere in our body. Okay, yeah, but this is the I think two-dimensional structure. This is secondary structure, and actually proteins are not, uh, you know, actually it's a has a three-dimensional structure, okay, and functions. So there have been a lot of research on protein. Okay, I'm not going into deep. Okay, yeah, you learn the details of protein in biochemistry. Okay. Anyway, the sequence is important. The important in this chapter is that these uh, proteins have many amino acids linearly connected. Okay, and important is that this amino acid are bases or acid, and at the same time it can act as basis. Okay, here you see uh, one more word on this heme. Okay, this ion. Actually, this is not a metal ion, not ion metal, but it is ion, divalent or trivalent. When it is coordinated to, it binds the oxygen atom, oxygen molecule. It is trivalent. Okay, and also it has high affinity toward carbon monoxide. You see, and this carbon monoxide now replaced the oxygen. Yeah? So if you are exposed to carbon monoxide, you may, it can be very serious. Okay, if carbon monoxide concentration is very high, and then you may die. Okay, so be careful. Okay, as I said, the proteins are composed of a lot of amino acid. Amino acid, they are individual amino acid. You know the structure of amino acid. Amino acid has, the amine group and carboxylic acid group, and also it has this one, a side group mm, called substituent. Okay, and this amino acid can be connected. Okay, through a peptide bond. Okay, here, let's see, these two amino acids are combined to make one molecule, right? In this case, um, water is removed. Okay, here, since there are one, two, three amino acids, so there are two peptide bond between the first two and between the last two. Okay. Mm. So when the peptide bond is formed, water molecule uh, is leaving. Okay, so here, uh, this water molecule here, there's oxygen from the carboxyl group, and there's hydrogen from this what amine group. Actually, it has a ammonium form here, and then this one, CO and NHA. Yeah? This one, this bond is formed. This is called the peptide bond, and the structure between of this part, okay, this part is planar, and this is very strong bond. All right. Okay, this way, amino acids are connected. Okay, long enough uh, to form the protein. Okay, but sequence is very important. Okay, you can learn more about that. All right. So amino acids are so important in our life. Okay, and important is that this amino acid are diprotic acid and bases. Sometimes amino acids are triprotic. Okay, at least diprotic, because that's be, uh, that's because amino acid structure itself, you um, can produce two protons or accept two protons. Okay, here this is general structure of amino acid. All right, this part is the same, but only different is the substituent part. Okay, by changing this substituent, you can synthesize actually, infinite number of amino acids. But in body, okay, in living things, there are only 20 amino acids. Okay, depending on which substituents are used. Okay, there are only 20 amino acids. Here, this amino acid have this carboxylic group, this functional group, and this ammonium group. Okay, yeah. And in a neutral solution, mostly this carboxylic, the proton here is going to this amine group. So this is a realistic structure, okay? But you can put this one hydrogen atom here, okay? That's the neutral form. This is actually this is a neutral form, yeah? But in solution, in aqueous solution, it exists as this form. Okay, yeah, look at that. This one, yeah? This is neutral form, but it carboxylic acid is this proton is rather a strong acid, right? So it dissociates and goes to this amine group. Okay, this is called Zwitterion. You know, Zwitter. In this is in German. Okay, that means two. Okay, you know the Einstein. Okay, fear of input, uh, like that. Anyway, so these amino acids are thoroughly studied. Okay, this figure is the gas phase structure of alanine. Okay, determined by microwave spectroscopy. All right, you just take a look, and you can have some three-dimensional image. All right. Okay, now let's consider how this one of amino acid, leucine, dissociate in aqueous solution. Okay, this is a neutral form of leucine. Okay, all right. Then substituent group is this one, and this leucine. Okay, when the solution becomes quite acidic, and then proton, it is protonated. Okay, here, this one, this carboxylate, this one is protonated. Okay, additional proton goes to this carboxyl group. But when the solution is what becomes basic, and this proton is detached, right? It dissociates, okay, from the structure. So the whole structure becomes negatively charged. Okay, yeah. So what we learn here is that the amino acid, if we start from this one, fully protonated form, you can dissociate not only once but twice. Okay, this one now dissociates, and then this ammonium proton is dissociates. Okay, so this one, the leucine, is called diprotic acid. Okay, yeah. So here, so let's yeah, leucine L. Okay, L means leucine. So fully protonated form is H2L plus. Yeah, it dissociates. Yeah, stepwise dissociation. And then this one HCl also uh, dissociates. Okay, the first one, this dissociation constant, uh, let's say this is Ka1 or K1. Okay, the second dissociation constant Ka2 or K2. And if we start from this fully dissociated form L minus, okay, when solution gets more and more acidic, it is protonated first to leucine HL and then H2L plus. Okay, here this is the equilibrium. L minus now accepts react with water, and it takes one proton from water. As a result, hydroxide ion is produced. Okay, so when L minus is dissolved in water, the solution is basic. Okay, likewise, when H2L plus dissociates in water, and the solution is acidic. All right. But what about the HCl is dissociates, okay, in water, and HCl takes react with water and takes proton, and generating hydroxide ion. Okay, but in this case, HCl now can dissociate. Okay? So it is not certain, yeah, at the moment, mm, whether the solution becomes acidic or basic, yeah, when um, the HCl, this neutral form, is dissolved in water. Okay. Anyway, so it dissociates stepwise. Okay? So relationship between Ka and Kb. Okay, this one Ka1. This one is conjugate to this this reaction. So Ka1 multiplied by Kb2, okay, is all the time Kw. Likewise, this middle form, okay, Ka2 multiplied by Kb1 is also Kw. They are, because they are conjugate pairs. All right. So the table 1 gives the 20 amino acid. Their dissociation constant. Okay. For example, alanine, the substituent group is a methyl group. Okay. And this carboxyl acid proton is all the time more acidic than ammonium proton. All right. So the pKa for carboxylic acid is smaller than the pKa for ammonium acid. Okay, you see. But sometimes the amino acid are triprotic. For example, aspartic acid, the substituent group is what? Carboxyl. It contains carboxyl group, and also this carboxyl proton, this hydrogen is uh, dissociates. Okay, so it is triprotic acid. All right. Yeah. In this case, this carboxyl acid dissociate first, and substituents proton dissociate second, and then this ammonium proton dissociates last. All right. Yeah, like that. I strongly recommend you memorize all the amino acids. They are only 20, and the symbol, okay, A, R, N, okay. All right. Yeah, and yeah, the list continues, okay. Isoleucine, leucine, lysine, like that, okay. Yeah. So this table is very important. Now we are ready to set out to calculate pH and composition of solutions. Okay, as usual, let's start from this acidic form, H2L plus. Okay, this is fully protonated, but here, don't think that when fully protonated amino acid is what it takes only plus one charge. No, it depends on amino acid. Okay, depending on the substituent group. When fully protonated, it may take you know what it may have divalent ion form. Okay, it depends. Right. Anyway, but that doesn't matter. Let's start from this form. Okay, this is a leucine case. Okay, when fully protonated, this leucine dissociates. This is first dissociation, and also there is a second dissociation. But since this first dissociation constant is much greater than second dissociation constant, okay, Ka1, or K1 is 4.69 times 10 to minus 3. All right. But what about the second dissociation constant? Right here, about 10 to minus 10. All right. Here, leucine here. The first dissociation constant, pKa, is quite small, but second one is quite large. So there is a big difference. Okay. So when we calculate pH for this form of leucine, so we can only consider this first dissociation. All right. Then now let's see. The initial concentration is 0.05 molar. Okay. Let's put X for proton. Okay. And then we write this quadratic equation. All right. Using this K1, and then we calculate the proton concentration or this HL form. Okay, now here X is 1.31 times 10 to minus 2 molar. Okay, So pH is 1.88. But what about the concentration of poorly dissociated form, which is uh, this one, L minus the form, okay, from K2, equilibrium constant. It is given by this equation, okay, and L minus form is given by this one, okay. Since we know the Ka2 and we know already this HL and proton concentration in this case, yeah, they are the same, yeah. So uh, this one, the fully deprotonated form of leucine, yeah, concentration is same as um, second dissociation constant, which is 1.79 times 10 to minus 10 molar. All right. So initial assumption, which is that the second dissociation uh, may be negligible. Okay. Yeah, that assumption is true because there is a really big difference. Look at that. The concentration difference between HL and L minus form. It is the difference is 8 orders of magnitude smaller. Yeah, this is a big difference. Yeah, that's the usual case. Okay, so we can say HL dissociation is negligible to give L minus. Okay, and what about the we have fully dissociated form of leucine, L minus. Okay, yeah, we can there is a compound sodium leucine. Okay, and then uh, we write these two dissociation equations. L minus now accept protons from water, giving rise to hydroxide ion, and equilibrium constant Kb1 is using this equation. It is about 5.59 times 10 to minus 5. But further, this HL now further takes proton from water, and then in this case Kb2 is quite small, 2.13 times 10 to minus 12. So difference is really great. So in this case we can only consider the first equilibrium. Okay, here when we have 0.05 molar in the L minus solution, and then we put X here. Yeah, we simply ignore the second dissociation, and then we can solve the equation for this one. Yeah? And then we get this X, in this case hydroxide ion concentration, which is now 1.64 times 10 to minus 3 molar. Okay, and what about the proton concentration using this relation? And then we get proton concentration, which is 6.11 times 10 to minus 12 molar. Okay, so pH is 11.21, right? And this one, L minus equilibrium concentration is given by this equation. This is a mass balance equation, and we get 4.84 times 10 to minus 2 molar, right? Yeah. And then what what is the concentration for fully protonated form? We can calculate from Kb2 here, okay, the second dissociation, okay, using this one, and then we get the concentration for H2L plus, which is 2.13 times 10 to minus 12. Yeah, this is a really low concentration. So our initial assumption, which is the first equation, is more important than second one. Now is proven true. All right. And then the intermediate form, and then I will give you the second separate lecture. Okay.